All right, Unit 8, 8.3, we're going to do a hypothesis test over means. So the last section was over proportions. Now I combined Z and T. So I didn't separate it this time. I think this is going to be better because we're going to take a long time to find the difference between the two. Okay? So let's review what a mean is. And when you hear the word mean, what do you think of? An average. What's the difference between that and a proportion?
Proportion is like a part.
Yeah, proportion is like a part of a whole, so it's usually written as a decimal or percentage. A mean can be any number. It could be bigger than 1. It could be negative. And it always has a standard deviation attached to it. So, or it could be, I wrote negative on here already. So bigger than 1, it could be negative. It always has a standard deviation attached to it in the problem. So that's how you'll be able to detect that it's a means problem.
Because proportion can be negative.
Right. Let's review the difference between Z and T. And this should not be there. I don't know why I have that there. Forgot to fill in. So if I have Z and I have T, I've got two columns. How do we know that something is Z versus something being T?
Population proportion.
Population what?
Our
Population standard deviation. Is known. Which is what symbol? Sigma, that little curly O. If we're talking about T, they're going to give us the sample standard deviation. And that's the symbol S. So if they give us, like if that standard deviation is attached to the population, that is going to be considered Z. Sometimes it has this symbol, and most of the time it does, but I have a few examples in here where it's not. You just have to read it and know that it's talking about the population. If the standard deviation is attached to the sample, then that means we're going to use T. So let's go through a few examples and try to decide whether it's Z or T. The mean SAT math reasoning score in 2007 was 515 with a standard deviation of 114. So here it gives me the standard deviation in the first sentence of the problem. And if you keep reading, then they took a sample of 40 students and found that the average was 540. Conduct an appropriate test. So we've got three numbers. 515, 114, and 540. This 515 right here is considered my what? My population or sample mean. So that's mu. It's our population mean. What is that 114? Sample or population standard deviation? Population, so that's sigma. And then this 540 right here is my X bar, my sample mean. So if I know sigma, then I'm going to use a Z. So Z test. Okay, read the next one. I'm going to circle the important numbers. Okay, that 28.76, what does that represent? Population mean, call that mu. 33 represents what? Sample mean, X bar, and 7.5, sample standard deviation. So that's the S.
So t-test.
So this would be a t-test. Good. Okay, last one. What's the 54? Mu. What's the 1030? Sigma. And the 5629? X bar. So population mean, population standard deviation.
Z-test.
So that would be a z-test. Good.
These are easy.
Okay, so we're going to go through the same steps. The only thing that is different is just the conditions and then adding in the T component, like the formula. So hypotheses, instead of P, now we have mu. So you can write as much or as little as you want, but essentially everything is the same. It's just now we're putting mu instead of P. And that's for Z and T. Yes?
Is there going to be the next lesson we're going to do it over standard deviation?
No, we're not going to ever do it over standard deviation.
Because isn't like the hypothesis?
Yeah, so we learned hypotheses with standard deviation, but we're not going to run any tests with it.
Okay.
So we're actually done with chapter 8 after this lesson.
Okay. Is the second one, would that be?
Left,
Okay.
and then the next one is right. So hypotheses are the same for Z and T. So you could write that if you want. They don't change. The conditions also are the same for Z and T. The only thing that's different is the formula. So, for conditions, random sample, and then we're checking one of the following. So the second condition is basically verifying that it's normal. Verify normality. And it could be because the population is normal, like it's given. Y'all kind of remember this from last unit a little. Or sample size is greater than 30, or we have to check the graph. And the graphs will be given to you.
Oh, good.
They will be.
Yeah. Solving for the test statistic. You don't have to write the definition again if you don't want to, because you already have it. But here are the differences between a z-test, and then a t-test. And the only difference in the formula is putting sigma or s.
Are we going to be given the formula? Or do we-
Yeah, you'll be given the formula. Yeah, so fix that to mean, sorry, if you wrote that down. Okay, step 4 is finding the p-value. You don't have to write the definition of p-value again if you don't want to, but you do need to have that memorized, like ingrained in your brain of what that is. So that's why I'm putting it on everything.
Different wording.
No, that is just the formal definition. So I can say it to you, but like
Yes,
you need
say
to
it.
memorize the formal definition, but the p-value is basically the probability of you, like whatever your sample mean is compared to your null hypothesis, like the population mean.
Okay.
Just basically how different they are
Okay.
is what your p-value is. It's like the probability of it if the population is true. So like the sleeping example I think they got was when they did the project, the population says that on average everyone gets 8 hours of sleep. And then you took a sample and you got 6 hours. So what the p-value is, like let's say you get 0.02, that means that if 8 hours of sleep is actually the real number, the chance of you taking a sample and getting 6 hours is only 2%. So you want that number to be really small because then that gives you evidence that since it's so small chance of happening that it's probably not right.
Okay.
The 8 is probably not right. So you have enough evidence to reject it. And so when we're solving for p-value, what function do we use in the calculator for z? To go from like test statistic to p-value, what calculator function do I use? Not inverse norm, normal CDF. So for the one on the left, I would type in normal CDF. And it's a right tail. So what would my lower bound be?
-2. The other number. No,
1.345 to infinity, and then 0, and then 1. If I have a t, and what did anybody do it? What do you get?
0.089313.
Perfect. If I have a t, not inverse t, but t CDF. T CDF in our calculator. So to get to that, we haven't done this before? Oh, so it's like normal CDF, but it's with a T. Yeah, I know, it's really fun. So you go to the second bars and it's option 6.
Do you have a calculator?
For Inspire, it's fine.
Charger,
Inspire, it's
Or
fine.
do you have a calculator?
but it's not Inspire because everybody stole them. So if it's a left, so the same process, like lower bound, upper bound, those rules are still the same.
You have a charger.
And if it's a left tail, that means I'm starting at negative infinity to negative 1.234. And you have to have the sample size in this because that depends on this third slot, which is your degrees of freedom. And y'all remember talking about degrees of freedom last chapter? It's always n-1. So if our sample size is 15, then 14 goes in this spot right here. So type that in.
0.118758773.
0.118.
75.
Oh, so 0.119.
Okay, Miss Thornhill.
Making a decision is the same. Conclusion is the same. You're just now talking about means. The rejection region, there is a typo there on my PowerPoint. What does it say for Z? Negative 2.392.
What about
Okay.
7 and 5 and 6?
They're the same. So if I were to do the rejection region approach, that's like finding the critical value and then deciding if it's in the rejection region or not. That's like the step 7. So let's just find the critical values using these significant levels and then decide if it's in the region or not. So with Z, we're going to use inverse norm. So we've got our Z curve, a 1% significance level, and it's a left tail test. So I would put in inverse norm of what? What percentile am I looking for?
0.01.
0.01, 0, and 1.
Negative 2.34.
Negative 2.326. So is this number negative 2.392? Is that in the region or not?
Yes.
Yes.
So you reject.
So I would reject the hoe. If I have a T score, still looks kind of like a normal curve, so I just draw it the same. And I have a 10% significance level to the right. So what percentile am I looking for here? 0.9. So I'm going to do inverse T of 0.90. And you also need a sample size, so I'm just going to make one up really quickly. N equals 23. Because that'll be given to you.
1.2 at mistake.
So what would I put? 0.9 and then what? 22. And you get 1.321. So this is 1.321. Is this T-score in the rejection region? No, it's to the left of it.
Failed to reject.
So I would fail to reject. Yeah, so my suggestion when you're going through these is to circle the important numbers, and I've got them up here. No, I've got it frozen. You've got your population mean, your sample size, your sample mean, and then standard deviation, depending on if it goes with population or sample. In this case, it's sample, so I'm going to put t-test.
We have the big-
Does anybody have questions about this write-up or concerns? It's not bad.
The Democrats use this stuff?
Uh-huh.
Okay, I
In this example, it gives me the population mean, which is what?
25.
No? 50.64. Gives it to me twice, so that's my mu. What else does it give me?
So you're in 12 stuff.
Population.
My n is 12, my sample size, and then what else?
Population.
Population standard deviation. So that means I'm going to be doing a what? A z-test. So it does give me 12 data points. So I'm going to put those into my list 1, and I want to calculate a mean from that, okay? So 1 bar stats, and I want to find what my x bar is, because I don't know what that is yet. So let's go ahead and put those into a list and figure out what the sample mean is. Okay, so my sample mean is 65.0142. You don't have to go out that many decimal places. Maybe 014 is sufficient. So everything is still exactly the same, except now our conditions, instead of saying that my sample size is greater than 30, we now talk about the box plot and the normal probability plot. So let's backtrack. Let's go through the hypotheses first. So my null hypothesis is what?
Mu is equal to.
Mu equals 50.64. My alternative is what?
Mu is
Not equal, because it says the word what? Different. Good. And what does mu represent? True mean what? What's the context? Monthly cell phone bill. Good. Conditions. The first condition is what?
Random sample, yeah.
Random sample. Random sample of what? 12 cell phone subscribers?
Sí, señor. Señorita. Sorry.
Cell phone users. Second one. So since it's not greater than 30, I have to comment on the graphs. And what am I looking for in the normal probability plot?
If the linear, then it's.
Okay, so normal probability plot is linear. What else? Box plot is what? Box plot has no outliers. / symmetrical. So what does that mean? Like, so what? So normal distribution. Okay, from here, formula, I'm going to use Z now, okay? So Z equals, my X bar is 65.0142 minus 50.64 divided by my standard deviation, which is 18.49, divided by the square root of what? 12. Okay, so go ahead and figure that out. The p-value, the conclusion, and rejection region. What is something that you're going to do with the p-value, though? Multiply it by 2. How come?
Because it's
Two-tailed.
Two-tailed. Perfect. So once you get your two, like those are called critical values. Once you get those, you take your test statistic, which is 2.693, and it falls within one of the rejection regions. So it's either in one or the other. But if it's at least in one, then
It isn't.
you reject.